everyone, and welcome back to Central Physics Reviews. Today, we're going to be extending our discussion from last episode of kinematics in one dimension into the world of multiple dimensions. And just to remind you what we did last time, we considered a system that had just one particle living on a one-dimensional line, and we could give it, for example, a position, let's call it x on this number line, and we said that its state at any given time consisted of a combination of its position at that time and its velocity at that time. So in the language of calculus, velocity was just the derivative of position with respect to time, or more conceptually, it's just how fast position was changing over time. And we didn't say why we considered that to be part of the state of this particle, but we said that those were just the rules of the game, right? And then we looked at the acceleration, which was given to us as a function of time, and the acceleration played the role of the laws of physics in this system. It allowed us to take some initial state, so some x0 and v0, at some initial time that we measured the system, and it allowed us to take that state and evolve it to any time we want. So we could find x of t and v of t, in other words, the state of the system at any time, not just this initial time. And the way we did that, just to remind you, was by integrating the acceleration to find how much velocity changed between the initial time and whatever t you choose. And then we integrated the velocity over time to find how the position changed in that time interval. So what changes when we go from doing kinematics in a one-dimensional system to a two-dimensional system, or even more dimensions? Well, we can obviously still put down a point over here in the two-dimensional plane and call it a position x, and we can still stipulate that the state of the system is the combination of the position x and the velocity v, which tells you how the position is changing over time. But one thing you'll notice is that these quantities, the position and the velocity, and as we'll soon see, the acceleration as well, can't be represented or expressed as just some number, right? If you want to tell me, for example, how my position is changing over time on this plane, it's not enough to say it's changing at 5 meters per second, for example. You also have to tell me which direction I'm moving in. So an example velocity would be not just some number, 5 meters per second, but also some direction, let's say down and to the right. And that would be associated with a speed or a magnitude of 5 meters per second. And this combination of direction and magnitude is something that we call a vector. And when we write down the variable v, which is a vector, we can denote that it's a vector by putting a little arrow on top of its head like that. What turns out to be really convenient is to treat not just the velocity, but also the position as a vector, or an arrow in this sense, right? Because any point on the two-dimensional plane is associated with an arrow that points from the origin to that point. And so because every position is associated with an arrow like this, we can treat position as a vector as well, which has some magnitude and some direction, right? So the magnitude would just be the length of this arrow, so that could be, for example, 3 meters. And the direction is, for example, in this case, just up and to the right. So now that we have our state defined, right, it's still position and velocity, but now we're talking about arrows or vectors instead of just numbers, we can go ahead and play the same game, right? If we know the acceleration as a function of time, which tells us how velocity and position change as a function of time, then we can go from some initial state, some initial vector x0, and some initial vector v0, to whatever final state we want, right? We go to some final x of t and v of t. So that tells us the vectors, or the arrows, that represent position and velocity at any given time. Now, one thing you'll notice is that acceleration itself has to be an arrow, right? If you're telling me how velocity changes over time, you have to tell me not just how much it changes over time, like 5 meters per second. You also have to tell me which direction it changes in. So that's why we represent acceleration as a vector as well. And as an example, we can have some acceleration vector be maybe straight to the left at 2 meters per second, right? Because it's describing how a velocity changes over time. Now, one advantage of using vectors in this way is that it gives us a really nice visual interpretation of how the acceleration sets up the evolution of our state over time. So if we look at the velocity vector, right now it's pointing down and to the right, but the acceleration is pointing to the left, which means that as time goes on, the velocity vector will start pointing more and more leftward. So maybe a second later, it points this way, and a second later, it points very, very slightly to the right, and a second later, it'll start pointing to the left, and it'll keep pointing more and more left as time goes on. Similarly, if the velocity starts out pointing down and to the right, our position vector will begin to move down and to the right. So for example, after a second, our position vector might instead look like this. And as our velocity vector starts to point just down, our position vector will keep moving down, maybe toward here. And then eventually the velocity vector will be pointing down and to the left, which means our position vector will start moving down and to the left. And so this is the key takeaway here. This is the nature of kinematics in multiple dimensions. Instead of thinking of position and velocity as just numbers that change over time according to the acceleration, position and velocity now become vectors or arrows in space, whose magnitudes and orientations are free to change over time, but still under the same laws of motion provided by the acceleration. Now, that's all well and good conceptually, but how do we actually do math with these objects, right? If we look at our fundamental calculus relationships between position, velocity, and acceleration, we see that velocity is the initial velocity plus some integral of acceleration, and position is some initial position plus the integral of velocity. And in multiple dimensions, each of these variables is actually a vector, not just a number. Right? Velocity is a vector, position is a vector, and acceleration is a vector that have directions in space. So what does it mean, for example, to write the velocity vector equals some initial velocity vector, which could be up and to the right with some magnitude, plus the integral of some acceleration, which could be to the left with some magnitude? Let's say it's constant, so it doesn't have to be a function of time, right? But we're integrating this from 0 to t, some acceleration vector dt. What in the world does this equation actually mean, and how do we actually implement it? How do we evaluate it? Well, this is where coordinate systems come in, right? And notice that fundamentally, at the very core of kinematics, there are no coordinates, right? These vectors were just objects floating around in space with some magnitude and some direction. A coordinate system, on the other hand, is something that you as a physicist are welcome to impose on a system in order to assign numbers to arbitrary geometric arrows or vectors. So here's an example. Let's say we take this initial velocity vector, right? Let's call it v vector. And let's say we want to assign a coordinate system to it in the standard way. So we have x pointing to the right and y pointing up. This is our coordinate system. And in these coordinates, what we can do is we can equate the vector v to a pair of numbers. One number that tells you how far along you are in the x direction. So this would be vx. And one number to tell you how far along you are in the y direction. So this would be vy. And these two numbers, as a coordinate pair in this way, are equivalent, given the coordinate system, to just specifying the object or the vector as a geometric arrow. But you're also welcome to choose any other coordinate system you like, right? We could have the same vector v pointing up and to the right, but let's say you want to choose a different coordinate system. Let's say we want to use coordinates where the x direction actually points up and to the right in the same way that v does. So we can have x pointing this way, and we can have y pointing perpendicular to it in this direction. Right? In this case, what happens is that the vector v is equivalent to, again, some component vx, which in this case, vx would be equivalent to the magnitude of v because it's entirely along the x direction. And we know that vy is going to be 0 because there is no component of this vector in the y direction, right? So you have new components, vx and 0 instead of vx and vy, but they represent the same geometric object because they're just in different coordinate systems. And in fact, if you wanted to, if you were braver than I am, You could even pick a coordinate system where x and y are not perpendicular to each other. There's nothing stopping you from doing that. It just turns out that oftentimes the math becomes harder when you don't use perpendicular coordinates. So just to recap, what a coordinate system does is it allows us to replace a geometric object, an arrow, with mathematical objects, with two numbers that are associated with two axes of our choice in this two-dimensional system. And doing the math of kinematics, doing calculus with pairs of numbers, is actually pretty straightforward. So if you remember, this is our general relationship that tells us what the velocity is, right? So this is the velocity vector at any time, starting from the initial velocity vector, v0, and adding the integral of the acceleration vector as a function of time, dt, right? So we add the integral to our initial velocity vector and we get our final velocity vector. But here we're dealing with numbers instead of pictures, so we can actually do math on it. And in particular, the way that math works with vectors that have multiple components, say an x component and a y component, is pretty straightforward, right? If you have some vector that has an x component of a and a y component of b, and you want to add another vector, let's say c comma d, then you end up with the very intuitive a plus c comma b plus d. So every component of the vector adds individually. What that means is that this simple equation that we have for the vector form of kinematics can be broken down into two separate equations, one for each dimension, right? So the first equation that we get is that Vx of t is equal to Vx0 plus the integral of from 0 to t of ax of t dt. And again, the way that we got this first equation was just by considering the left component of every vector, because as I just showed you, they add individually or separately. Right now, if we consider the right component of every vector, then what we get is an analogous equation for vy of t, right? Vy of t just becomes, Vy of t becomes Vy0 plus the integral from 0 to t ay of t dt. And what you'll notice is that this is really cool because the combination of, for example, vx and vy into a vector was difficult to do math with because that was basically just an arrow. But here we separated out vx and vy into separate equations, and in this context they're just numbers, right? Vx is a number and vy is a number. Similarly, ax is a number and ay is a number. We're now dealing entirely with numbers, and this problem is broken down into the same exact problem we had in one-dimensional kinematics, where everything was a number. Now we can keep going, right? We can say that because we have this equation for vx of t, then we can analogously derive the position over time, right? So the x component of the position is going to equal the initial x component, x0, plus the integral from 0 to t of the x component of the velocity, vx of t dt, right? And that's just through the perfectly analogous process to what we just did, going from acceleration to velocity. You can do that again and go from velocity to position. And so the y component of position in this case will be y of t equals y0 plus the integral from 0 to t vy of t dt, right? So that comes from these respective equations. And so just by following the math, intuitively what just happened here is that a two-dimensional problem turned into two completely separate one-dimensional problems, right? The math tells us that if we have a two-dimensional problem, one way we can solve it is by treating the x components of the system completely separately on the left-hand side here, and treat the y components of the system completely separately like on the right-hand side here. And those two problems are completely separable or independent one-dimensional kinematics problems that we already know how to solve from last time. And what this means is that the same shortcuts for constant acceleration that we talked about last time apply here to each individual dimension, right? So on the left-hand side, we have all the shortcuts for the x-dimensional problem, right? So we have vx equals vx0 plus axt, and we have all of the equations that we had before for constant acceleration, but only considering the x component of our vectors. And on the right, we have the same exact equations that I basically copied and pasted, but every index or every dimension was replaced from x to y, because that's just a separate problem in this approach to two-dimensional kinematics. Now again, just to emphasize, what we mean by x and y is completely arbitrary and completely up to you. You can choose the x dimension to point in any which way you want, as long as the y dimension that you choose points somewhere different, probably somewhere perpendicular to it would be best. But in principle, it doesn't have to be to the right and up. It can be any two directions you like. Now, of course, there's still a very real physical sense in which these two problems aren't completely separate from one another, and mathematically we see that in the fact that they share a common time variable, right? At any given time, that controls both what the x-dimensional trajectory is and what the y-dimensional trajectory is, right? You can't break time into different components for each dimension. That's not how it works. What this does is it opens up the door to more shortcuts that allow us to cross over between the x dimension and the y dimension. So for example, we can say, if we know what our y coordinate is, can we use a shortcut to directly figure out what our x coordinate is at precisely the time that would give us that y coordinate in our trajectory? And the most common application of this is something called the range equation, right? So this is going to be a very particular setup, a very special system, where our acceleration is again constant. So our acceleration vector as a function of time is just a constant vector. And we're going to have it point down, right? There's no better direction than down. Any direction is equally fine for the range equation, but for our example, let's just have it point down. And what we're going to do is we're going to define our coordinate system in a very convenient way so that the acceleration actually points along one of the axes. So we're going to just choose the standard way of defining coordinates with x going to the right and y going up, so that our acceleration points precisely in the minus y direction. What that means is that if the magnitude of the acceleration is some number a, then this vector is equal to 0 in the x direction and minus a in the y direction, right? Because y points up, but the acceleration points down. Okay, so those are the laws of motion per se, but what's the problem that we're trying to solve? Well, we actually have a very particular problem. We're trying to find how much the x component of our position changes. So we're trying to find delta x when delta y over time is equal to 0. So, if I were to illustrate this, what typically happens is you have some initial level for y. So this is y0, where we initially start. And as long as we have some sort of initial velocity that points upwards, so let's say this is our v0 vector, as long as we have some initial velocity that points upwards, what's going to happen in this system is the acceleration is going to eventually make the velocity point downwards, and our particle is going to follow a trajectory in which, even though it starts moving up, it's going to eventually come back down and land at the same position where it started. It doesn't have to stop moving there, but in this problem, we're interested in what happens, or more specifically, we're interested in how far it travels in the x direction by the time it comes back to its original level of y. Right now, from our one-dimensional kinematics equations, we know that delta x can always be written as v0xt plus 1/2 axt squared. But what's really cool about this system is that the x component of the acceleration is actually 0, right? Acceleration is entirely along what we defined to be the y-axis. So we're going to just get rid of that part and leave delta x equals v0xt. Now, of course, we're not given off the bat how much time this particle has been traveling for. What we're given is how much it moved in the y direction, namely, it came back to its original y position, right? But time is what links x and y. So what we're going to do is we're going to solve for the time at which the y position is back to where it started, and just plug that into this equation for delta x, right? So we have delta y equals v0yt plus 1/2 ayt squared. That's our one-dimensional kinematic equation for the y direction. And we're just going to set that equal to 0 so that we can solve for what time this actually occurs at. right? And in particular, we can factor this equation, so we can get a factor of t out here, multiplying v0y plus 1/2 ayt. And we get 2 times at which delta y is 0, right? We get the first time, that's t equals 0. Of course, when t equals 0, delta y equals 0. That makes sense. But then we also get the second time, t equals, let's see, so we would have to first bring v0y to the other side. We get v0y equals minus 1/2 ayt. And so if we solve for time, we get that it's equal to 2 v0y divided by ay with a minus sign. And what we can do is actually plug in the fact that ay is minus a from this equation way up here, right? That's just how we defined our acceleration. So that minus sign takes care of the minus sign we have right now, and so our time is equal to 2 v0y over the magnitude of the acceleration, a. So as I promised, we can plug this back into delta x, and what we find is that delta x is equal to 2 v0x v0y divided by the magnitude of the acceleration. So there are a couple other ways to write this if you like, for convenience, right? You can, for example, write 2 times v0 magnitude squared, right? So just to remind you, v0 squared as a whole is equal to v0x squared plus v0y squared. That's just the Pythagorean theorem. So if we just factor out v0 squared, what we can do is we can replace v0x with v0x over v0, and we can multiply that by v0y over v0, and that's all still over a. And then this brings us to the standard form, where we can replace v0x over v0 with just some sort of cosine theta, right? So if we have some angle theta over here, maybe I should draw this a little bit bigger. If we have a big vector v0, and we have some angle theta to the x-axis, then what we can always say is that v0x is v0 times cosine theta, and the y component over here is v0y is v0 sine theta. That just comes from trigonometry and the definitions of sine theta and cosine theta, right? So using that, we can replace v0x over v0 with cosine theta, and v0y over v0 with sine theta. And then there's this identity where 2 times cosine theta times sine theta is just equal to the sine of 2 theta. So the standard form for writing the range equation is you keep the v0 squared, and you replace the rest of the numerator with sine of 2 theta. And then you're still dividing by a. Now I don't want to get too lost in the details of using coordinate systems and working with shortcuts that are only true when acceleration is a constant vector. So let's go back and summarize some of the key concepts that we talked about in this video about two-dimensional kinematics. The first thing that we noticed was that in 2 dimensions, or even more dimensions, as many dimensions as you like, the position, velocity, and acceleration variables are treated as vectors, or arrows in space, I should say, instead of just numbers. The second thing we talked about was that to do math with these vectors, we can impose a coordinate system. We can define a direction of our choosing to be x and another direction of our choosing to be y, and use coordinates, or in other words, projections of how much of a vector is aligned with x and how much is aligned with y, to actually do math and calculus with those geometric arrows. Finally, the last thing we talked about was that the motion along each coordinate, so x versus y, is independent, so that you can solve the x trajectory completely on its own, and you can solve the y trajectory completely on its own. But they're also linked through time. So if you know the y trajectory, you can use information about where you are in terms of your y coordinate to actually get information about where you are in terms of your x coordinate. And that's exactly what the range equation did in the very specific context of constant acceleration. So hopefully this explanation gave you a little bit more intuition, a little bit stronger understanding of what exactly it is that we're doing when we're working with multidimensional kinematics. It's really nothing more than looking at the arrows that represent the state of our system and using the arrow that is the acceleration to figure out how those arrows change over time. And then, of course, the mathematical part is using coordinates to turn those arrows into numbers that we can do math with. If you like this video and you want to keep watching, if you want to know why the state of the system is its position and its velocity, but not its acceleration, then go ahead and subscribe, and I look forward to seeing you in the next video where we're going to finally dive into dynamics and Newton's laws of motion.